Paper 1, June 2019, a big transition metal question here, so we might have to refer to our table. FeH2O6 3+, so it's a 3+ ion, so we're looking at iron 3, forms brown precipitates, FeH2O3 OH3, forms brown precipitates with sodium hydroxide, also with ammonia, also with sodium carbonate, always forms this brown precipitate, FeH2O3OH3. It's also acidic, it's 3+ and acidic. We've mentioned how it withdraws electrons along the H2O bonds and releases H+ and leaves OH-. That's how it does it, and it releases H+ by breaking those bonds, those waters. 3 of the waters break off into OHs and an H+, OH- and H+. So let's have a little look then. So what's it doing? It's asking precipitate J with sodium carbonate. So with sodium carbonate, we know we're making FeH2O3OH3 as a solid, Fe3+, no charges on the waters, 3 OH1- to leave no charge overall. It's going to be a solid. So J is FeOH3H2O3, or you can put it the other way around as we've done in the table, FeH2O3OH3. Carbonate, I put it as carbonate ions rather than putting sodium carbonate, just because I thought that was easier to leave the sodiums out. Sodium carbonate, carbonate ions, CO3 2-. If it's acidic, then carbonate ions and acids will make carbon dioxide. What else is going to be released? 3 waters. Tricky equation that, and you've got to balance it as well. Hard to get 3 marks on that. Give the formula of L and the equation for reaction 2. Reaction 2, concentrated HCl, so you're going to get 4 Cl ligands around the Fe. If Fe is 3+ and the Cl's, there's 4 of them, 3+ and 4- leaves 1- left over. That's why it's a solution. It's a green colour. So only 4 can fit around rather than 6 waters because the Cl's are larger. And therefore you've got the equation there, FeH2O6 being released. And it's going to go ahead because you've got 5 molecules on the left, 7 on the right, and you get a positive entropy change as it goes left to right. And a nice green colour for anything with Cl ligands around it. Suggests a reagent for reaction 3. I need a reducing agent, something that turns Fe3+ down into Fe2+, oxidation state 3 down to 2, and a reducing agent for transition metals is Zn. You need it in sulfuric acid, but Zn will get you the mark. A big question, we've done this several times, give the formula of precipitate M and say its colour. What was this? M. Concentrated ammonia with Fe. Concentrated ammonia with Fe. So we know that ammonia again forms, replaces some of the waters, 2 of the waters with OHs, Fe2+, 2 OH1- to leave no charge left over, and it's a green precipitate. So it should be a green precipitate, precipitate M, a green precipitate of FeOH2, H2O4, or as I say, you can put them the other way around, FeH2O4 OH2, a green solid, a green precipitate. Transition metals, so we've done this question several times over. You've got cobalt and you've got platinum, and you've got to talk about all the different ways that the ligands can form different complexes with different shapes. So you could have cobalt with 6 waters all around it. That would be octahedral, coordination number 6, shape octahedral, bond angle 90. Or you could have Cl's around it, 4 of them, that would be tetrahedral. If it's CO2+, CO cobalt 2+, 4 Cl1- leaves 2- left over, a nice tetrahedral shape. Coordination number now 4 with 4 coordinate bonds around it, bond angle 109.5. Cisplatin, you need to know platinum has 2 lone pairs, one up and one down. and it forms square planar shapes. So you can have two Cls together and two NHs together. That's called cisplatin. Cis means together, sometimes called a Z isomer, but in this case cisplatin, used as a cancer drug. And then you could have them opposite, transplatin, with the two Cls opposite and the two NH3s opposite. Coordination number 4, because there's 4 coordinate bonds, bond angle 90, square planar shape, because the two lone pairs up and down force the 4 bonding pairs into a square planar shape. And then there are others as well. So I've done cisplatin and transplatin to show that it can be cis and trans, so those are geometrical isomers of each other, or you can call them cis and trans, or Z and E. And then finally I've done one with two OHs replacing two other waters, and you can have them together or opposite, and again that's a geometrical isomer where you've got Z and E, Z being together and E being opposite, or you could say cis together and trans opposite. Either way, it doesn't matter whether you use cis and trans or Z and E. Geometrical isomers again with the same structural formula but different positions of atoms in space.